November 1944. A secret facility in Teddington, England. British metallurgists place a sample of captured German U-boat hull steel into a pressure chamber. This steel was supposed to withstand depths of 280 meters. The steel that protected Germany's most feared weapon. The steel that had terrorized Allied convoys for 5 brutal years. They begin the test. At 140 meters equivalent pressure, something catastrophic happens. The steel doesn't bend. It doesn't gradually deform. It shatters, like glass dropped on concrete. In that single moment, the British discovered why U-boats were mysteriously imploding at depths they should have survived. But this discovery revealed something far more terrifying. The problem wasn't just in the steel. It was in the fundamental approach to submarine construction that Germany had been using since the war began. What the engineers found would change submarine warfare forever. But first, we need to understand how Germany created the most feared naval weapon of World War II, and why its greatest strength concealed a fatal weakness that no one saw coming. To understand what the British discovered, you need to understand what a U-boat actually was, and more importantly, what it represented to both sides of the Atlantic War. By 1939, Germany had learned hard lessons. From World War I, the U-boat had nearly starved Britain into submission between 1914 and 1918, over 11 million tons of Allied shipping sent to the bottom. But they lost, and the Treaty of Versailles stripped Germany of its submarine fleet entirely. When Hitler began secretly rebuilding Germany's navy in the 1930s, submarine development became an obsession. Not just any submarines. They needed vessels that could operate far from home ports, strike without warning, and vanish before counterattack. The Type 7 U-boat became Germany's answer. Compact, mass-producible, deadly. 67 meters long. Displacement of 769 tons on the surface. Crew of 44 men crammed into a steel tube, barely 4.7 meters in diameter at its widest point. These weren't comfortable vessels. They were weapons, every cubic centimeter optimized for one purpose: sinking Allied shipping. The Type 7 could carry 14 torpedoes. It had a range of 8,500 nautical miles at cruising speed. And critically, it had a rated maximum operating depth of 220 meters, with a theoretical crush depth somewhere around 250 to 280 meters. That crush depth rating wasn't arbitrary. It represented the point where hydrostatic pressure would overcome the structural integrity of the pressure hull. Below that depth, the submarine would implode. The hull would collapse inward in milliseconds. Everyone inside would die instantly. The pressure hull itself was an engineering marvel. Circular cross-section throughout most of the boat's length. This shape distributes pressure evenly. The hull consisted of 18-millimeter thick steel plates, reinforced internally with strengthening ribs every 700 millimeters. The steel specification called for tensile strength of 74,000 pounds per square inch. Yield point of 51,300 psi. On paper, this should have been more than sufficient. Germany's shipyards in Kiel, Hamburg, Bremen, and elsewhere produced these boats with industrial efficiency. By 1942, they were launching U-boats faster than the Allies could sink them. The production system involved modular construction, hull sections built separately, then welded together. This approach drastically reduced construction time. A Type 7 could be built in about 6 months. Compare this to the years required for a battleship or cruiser, and you see the strategic genius. Germany couldn't match Britain's surface fleet, but they could flood the Atlantic with submarines. And for the first 3 years of the war, it worked terrifyingly well. Britain is an island. This simple geographic fact shaped everything about how World War II would be fought in Europe. Britain imported 70% of its food, nearly all its oil, most raw materials for weapons production. Everything came by ship across the Atlantic from North America and the Empire. Admiral Karl Dönitz, commander of Germany's U-boat fleet, understood this vulnerability perfectly. His strategy was brutally simple: sink merchant ships faster than the Allies could build them. Starve Britain. force them out of the war before America's industrial might could tip the balance. He called it the Tonnage War. And by early 1940, Germany was winning. The U-boats hunted in wolf packs, groups of 8 to 20 submarines coordinated by radio, guided to convoy positions by long-range reconnaissance aircraft or radio intercepts. When they found a convoy, they struck at night on the surface, where their diesel engines gave them speed advantage over the merchant ships. The statistics were horrifying. In 1940, U-boats sank 2.4 million tons of Allied shipping. In 1941, 2.3 million tons. In 1942, 6.2 million tons. That's over 1,000 ships. Thousands of sailors drowned in the freezing North Atlantic. Supply lines strangled. Britain's food reserves dwindled to a few weeks' supply multiple times during the war. From the German perspective, these were the golden years. U-boat commanders like Günther Prien, Otto Kretschmer, and Joachim Schepke became national heroes. They returned to French ports flying victory pennants showing tonnage sunk. Propaganda newsreels celebrated their triumphs. Young men volunteered for submarine service in droves. But the British were learning. Slowly, painfully, they developed countermeasures. The convoy system matured. Merchant ships traveled in large groups protected by destroyers and corvettes. Long-range aircraft began covering the mid-Atlantic gap. Radar improved, allowing detection of surfaced U-boats at night. Code breaking at Bletchley Park revealed German dispositions, and most critically for our story, depth charges improved. Early depth charges were crude. Barrel-shaped explosives rolled off a ship's stern, set to detonate at a specific depth. The problem was accuracy. A U-boat could hear the attacking ship's propeller sounds and take evasive action. Even a near miss wasn't always fatal. The submarine's pressure hull was designed to withstand external pressure from all directions. A depth charge explosion created a pressure wave, but unless it detonated very close, the U-boat might survive with damage. By 1943, the Allies introduced the Hedgehog. This forward-throwing weapon fired 24 contact-fused projectiles ahead of the attacking ship. If any struck the submarine, detonation was practically guaranteed to be fatal. The Hedgehog achieved a kill rate of about 1 U-boat for every 5.7 attacks. Compare this to conventional depth charges. 1 kill per 60.5 attacks. Then came the Squid, even more devastating. 3 mortars, firing heavy charges in a triangular pattern, timed to detonate simultaneously around the predicted submarine position. The Squid sank 17 U-boats in just 50 attacks, a success rate of 1 in 3. Suddenly, German U-boat losses spiked. May 1943 became known as Black May in the Kriegsmarine. 41 U-boats lost in a single month. Donitz temporarily withdrew the wolf packs from the North Atlantic. The hunters had become the hunted. But here's what puzzled the British naval intelligence analysts and the crews who survived U-boat attacks. They were finding wreckage at depths that didn't make sense. When a depth charge sinks a submarine, there are patterns. Experienced anti-submarine warfare officers knew what to look for. Oil slicks rising to the surface. Debris. Sometimes bodies. Often pieces of the submarine's outer hull plating. Equipment. Personal effects. But some wrecks told a different story. The debris pattern suggested catastrophic structural failure at relatively shallow depths. Depths well within the U-boat's rated operating parameters. At first, they attributed it to direct hits by depth charges, or multiple near misses causing cumulative damage. But as the war progressed, and more U-boats were sunk, more data accumulated, and a pattern emerged that demanded explanation. Interrogations of captured U-boat crews provided critical intelligence. Survivors described diving deeper than authorized limits during desperate evasion attempts. Some boats had reportedly reached 280 or even 300 meters and survived. But others reported hearing terrifying sounds, sudden implosions of sister boats at depths that should have been survivable. One particularly valuable intelligence source came from captured U-boat officers. They described construction quality declining as the war progressed. Earlier boats, built in 1939 and 1940, were constructed to exacting peacetime standards. Experienced welders, proper inspection, time for quality control. But by 1942 and 1943, production pressure intensified. Germany needed submarines faster. Welders were rushed. Inspection procedures shortened. Slave labor, including concentration camp prisoners, worked in some shipyards. The quality couldn't match pre-war standards. Still, this didn't fully explain what the British were seeing. Even earlier U-boats, well-constructed boats, were showing signs of unexpected structural weakness. The breakthrough came when several U-boats were captured intact, or nearly intact. The most famous capture was U-505 by the U.S. Navy in June 1944. But the British had their own prizes. U-570, captured in 1941. U-559, boarded in 1942, before sinking, yielding priceless Enigma materials. And others, these captured boats allowed direct examination. British naval architects and metallurgists finally had access to the actual steel, the actual construction methods, the actual welds. They could test everything. What they discovered would reshape their understanding of submarine warfare. But more than that, it would reveal a fundamental materials science problem that nobody in the world fully understood yet. Not the Germans, not the British, not the Americans, a problem that was also affecting Allied ships in a completely different way. The facility in Teddington wasn't particularly impressive from the outside. Located in southwest London on the banks of the Thames, the National Physical Laboratory had existed since 1900. During peacetime, they calibrated instruments, established measurement standards, conducted basic research. During wartime, they solved urgent problems. And in 1944, submarine metallurgy became an urgent problem. The British Navy provided samples of hull steel taken from captured and salvaged U-boats. The metallurgists also had samples from their own submarine construction for comparison. The question was straightforward. What were the actual material properties of German submarine steel? The testing methodology followed established protocols. Tensile testing to measure strength, hardness testing, chemical analysis to determine composition, and critically, impact testing to measure toughness at various temperatures. Tensile testing came first. They machined test samples into standardized shapes, then pulled them apart in a testing machine while measuring the force required and how much the material stretched before fracturing. This revealed tensile strength, yield strength, and ductility. The German steel performed well in these tests. It met its specifications. Tensile strength around 74,000 psi, yield point around 51,000 psi. Nothing alarming. There, chemical analysis showed the steel composition was typical for submarine-grade pressure hull material. Iron, of course, carbon content around 0.15 to 0.20%. Small amounts of manganese, silicon, and other elements for strength and workability. Some sulfur and phosphorus, which were difficult to eliminate entirely from steel-making processes of that era. Again, nothing unexpected. The steel composition was similar to what the British used in their own submarines. But then they conducted Charpy impact tests. This test measures how much energy a material can absorb before fracturing when struck suddenly. A small notched sample is placed in the testing machine. A heavy pendulum swings down and strikes it. The height the pendulum reaches on the opposite side indicates how much energy the sample absorbed. Ductile materials absorb significant energy. They bend, deform, absorb the impact. The sample doesn't break cleanly. You see evidence of plastic deformation. The fracture surface looks fibrous, torn. Brittle materials absorb little energy. They shatter. The fracture surface looks crystalline, flat, sharp-edged. The British metallurgists tested the U-boat steel at room temperature first. Good energy absorption, ductile behavior, exactly what you want. Then they tested at lower temperatures. This is where everything changed. At around 5 degrees Celsius, the steel's behavior transformed. Energy absorption dropped dramatically. Instead of bending, the sample shattered. The fracture surfaces changed from fibrous to crystalline. The steel had undergone what metallurgists call a ductile to brittle transition. This transition temperature was far too high. Submarine steel needs to remain ductile at 0 degrees Celsius, even below zero. The North Atlantic regularly drops to 0 to 5 degrees Celsius. In winter, it can be colder. They tested multiple samples from different U-boats. The results were consistent. Above about 5 to 10 degrees Celsius, the steel was reasonably tough. Below that temperature, it became dangerously brittle. Now they understood. Now the unexplained implosions made sense. Imagine you're commanding a U-boat in the North Atlantic. Winter, 1944, water temperature near freezing. You're under attack by a destroyer. Depth charges exploding around you. You dive deeper. 150 meters, 180 meters, 200 meters. The pressure at 200 meters is enormous, about 20 times atmospheric pressure. That's 290 psi pressing inward on every square inch of the hull. The cylindrical pressure hull is designed to withstand this. The circular shape distributes the load evenly. The internal frames prevent buckling. Under normal conditions, the steel has enough strength and enough ductility to handle the stress. But your hull has been at near freezing temperature for hours. The steel has undergone that ductile to brittle transition. It's no longer tough. It's hard, but brittle. Somewhere in the hull is a small defect, a tiny crack at a weld, or a region where the steel has slightly different properties. Maybe a region with slightly higher carbon content, or an area affected by welding heat, or a rivet hole with a sharp edge, or a junction between hull plates that creates a stress concentration point. Under normal circumstances, if that crack started to grow, the ductile steel would deform locally. The crack tip would blunt. Energy would be absorbed through plastic deformation. The crack would stop growing, but in brittle steel, something different happens. The crack doesn't blunt, it stays sharp. It concentrates stress at its tip, and when the stress exceeds the material's strength, the crack doesn't slowly grow. It propagates, fast, at nearly the speed of sound in steel. This is called brittle fracture. And once it starts, it's unstoppable. The crack races through the hull. The pressure hull is under tremendous load from the water pressure. As the crack spreads, that load redistributes to the remaining material, increasing stress further. This accelerates the crack even more. In milliseconds, the crack can traverse the entire circumference of the submarine. The hull fails catastrophically. Hundreds of tons of steel collapse inward. The water pressure instantly crushes everything inside. The men inside don't suffer. At least there's that. The collapse happens faster than nerve signals can travel to the brain. Faster than consciousness. One moment they exist, the next moment they don't. This can happen at depths well within the submarine's rated capacity. Because the rated crush depth assumed ductile behavior, it assumed that local overstress would cause yielding, not catastrophic fracture. The colder the water, the more brittle the steel, the more likely this failure mode becomes. And the North Atlantic in winter is very cold indeed. The British had discovered the U-boat's fatal weakness, but understanding a problem and solving it are different things. The obvious question is why? Why did German submarine steel have this weakness? Were the Germans ignorant of metallurgy? Were they cutting corners? The answer is more complex and more troubling. Because the truth is, in 1940, nobody fully understood brittle fracture in welded steel structures. The metallurgical theory existed. Scientists knew that some materials became brittle at low temperatures. They knew about crystal structure transitions in metals. But translating that theoretical knowledge into practical design criteria for large welded structures was a different challenge. The key problem was impurities in the steel, particularly sulfur and phosphorus. These elements were present in the iron ore and coal used in steelmaking. Removing them completely was difficult with 1940s technology. Some amount always remained. Sulfur and phosphorus tend to segregate at grain boundaries in steel. At these boundaries, they weaken the bonds between iron crystals. At higher temperatures, this isn't critical because the steel can deform plastically. But at lower temperatures, when the steel wants to behave brittly, these weakened grain boundaries become fracture paths. The carbon content also mattered. Higher carbon increases strength but decreases toughness, especially at low temperatures. German submarine steel had moderately low carbon, but combined with the impurities, it was enough to push the transition temperature too high. But here's the critical part. The Germans tested their steel. They had specifications. They checked that the steel met strength requirements. So how did this problem slip through? The answer lies in the testing methods. Most steel testing at that time focused on room temperature properties. Tensile strength, hardness, and similar measurements at 20 degrees Celsius or so. Low-temperature impact testing was less commonly specified. Additionally, the Germans pressure-tested completed submarines in a test dock at Kiel. They pressurized the hull to simulate 90 meters depth, sometimes more. These tests verified that the hull could withstand the pressure, but they were conducted with warm submarines in relatively warm dock water. They didn't replicate the combination of cold temperature and high pressure that occurred in the North Atlantic. It's also worth noting that submarine steel wasn't uniquely German in having this problem. The British and Americans were discovering similar issues in other contexts. Liberty ships, the mass-produced cargo vessels built by the United States, were splitting in half due to brittle fracture. The SS Schenectady famously broke completely in two while docked in January 1943. Many Liberty ships developed cracks in cold water. The Liberty ship problem had different causes, primarily related to welding practices and stress concentrations at square hatch corners. But the underlying material behavior was the same: steel that became dangerously brittle in cold water. What made the U-boat situation particularly severe was the operating environment. Submarines regularly operated at the edge of their structural limits. A surface ship with a crack might survive and limp to port. A submarine at depth with a crack faces instant catastrophic failure. Germany did attempt to address quality issues as the war progressed. They improved welding procedures. They tried to better train welders. They implemented more inspections. But these measures addressed workmanship, not the fundamental material properties. Changing the steel composition would have required retooling the entire supply chain. Different ore sources, different refining processes, extensive testing of new alloys. Time Germany didn't have. And even if they'd had time, the necessary metallurgical understanding to specify better steel for low-temperature service was only just developing. So, the weakness remained. And the British now knew about it. Knowledge is power, especially in warfare. Once British naval intelligence understood the U-boat's vulnerability, they could adapt tactics to exploit it. The immediate application was in depth-charge warfare. Attacks were concentrated in cold water regions, particularly during winter months. The logic was straightforward. Cold water meant brittle hulls meant lower effective crush depth. Anti-submarine commanders received briefings on structural vulnerabilities. They were encouraged to force U-boats deeper, drive them toward their limits. Even if a submarine survived the initial depth-charge attack, the stress of deep diving in cold water might cause spontaneous structural failure. The hedgehog and squid weapons became even more valuable. These contact-fused weapons didn't need to sink a U-boat directly. Damage to the hull, even relatively minor damage that created cracks or stress concentrations, could be fatal if the submarine then attempted to dive deep to escape. Intelligence also affected strategic planning. Operations were timed to coincide with winter months when possible. Areas with particularly cold water became preferred hunting grounds for anti-submarine groups. But the British were careful not to reveal what they knew. If Germany realized that the Allies understood the steel weakness, they might implement emergency changes or at least modify operating procedures to compensate. So the knowledge remained classified. Highly classified, even within the Royal Navy, The information was compartmentalized. Ship commanders might know that deeper attacks were more effective in cold water, but not necessarily why. The detailed metallurgical findings remained restricted to a small circle of engineers, intelligence analysts, and senior commanders. The Germans, for their part, did notice unusual loss patterns. Operational analyses showed that U-boats were being lost at higher rates in certain areas and certain times of year. But they attributed this primarily to improved Allied anti-submarine capabilities. Better radar, better sonar, better weapons, more escort ships, more aircraft. They weren't entirely wrong. All those factors contributed. The metallurgical weakness was one element among many, but it was a hidden element that the Germans couldn't see or counter. Some U-boat commanders suspected there was more to the story. Reports from survivors sometimes mentioned unexplained structural sounds during deep diving. Creaking and groaning was normal. The hull flexed under pressure. But some sounds were different. Sharp cracks, sudden pops, things that suggested material failure rather than elastic deformation. A few commanders made unofficial decisions to limit diving depth more conservatively than regulations specified, especially in cold water. But official policy didn't change. The submarine's rated depths remained 220 to 250 meters depending on type. Meanwhile, German submarine development continued with more advanced designs. The Type 21 electroboot, introduced late in the war, featured a different hull design with higher crush depth, better hydrodynamics, and much larger battery capacity for sustained underwater operation. These boats addressed many tactical weaknesses of earlier designs, but even the Type 13 used steel with similar material properties. The fundamental brittleness issue remained, and by the time they entered service in early 1945, it was too late to affect the war's outcome. The U-boat steel story is more than just a historical curiosity. It represents a critical lesson in engineering, one that would reshape materials science and structural design for decades to come. The central insight is this: strength alone isn't enough. A material can be incredibly strong in terms of how much stress it can withstand, but still fail catastrophically if it's not also tough. Strength and toughness are different properties. Strength is resistance to deformation under load. Toughness is resistance to crack propagation. You can have high strength with low toughness. That's exactly what happened with cold U-boat hull steel. This distinction sounds academic until you're responsible for designing structures where failure means death. Then it becomes intensely practical. After World War II, the maritime industry completely rethought how they specified steel for ships. Low-temperature toughness became a mandatory requirement. Charpy impact testing at service temperatures became standard practice. Steel mills developed new grades specifically designed to resist brittle fracture. The submarine forces went even further. Cold water testing protocols were developed. New alloys were created. HY80 and HY100 steels, developed in the 1950s and 60s, provided much better performance. These high-yield steels combined strength with excellent toughness, down to very low temperatures. Modern submarine steel specifications are exhaustive. They specify not just strength and composition, but toughness at specific temperatures, weldability, fatigue resistance, and corrosion behavior. A single batch of steel might undergo dozens of different tests before being approved for pressure hull construction. The lessons extended beyond submarines. Pressure vessels, pipelines, offshore platforms, and aircraft all benefited from the improved understanding of brittle fracture. Entire fields of study developed around fracture mechanics, the mathematical framework for predicting when and how cracks will grow in structures. One of the most famous researchers in this field was Constance Tipper, a British metallurgist who studied the Liberty ship failures. Her work helped establish the science of fractography, analyzing fracture surfaces to determine failure mechanisms. She demonstrated conclusively how brittle fracture initiated and propagated in welded steel ships. By the 1960s and 70s, fracture mechanics had become a mature engineering discipline. Designers could calculate stress intensity factors at crack tips, predict crack growth rates, and specify inspection intervals to ensure structures remained safe throughout their service lives. The U-boat story also highlights the importance of service environment in design. It's not enough to test a component in ideal laboratory conditions. You must test it in conditions that replicate actual operating environments. Temperature, pressure, loading rates, cyclic loading, corrosion, everything matters. Military procurement agencies learned this lesson repeatedly through hard experience. The U-boat hull steel, Liberty ship fractures, aircraft crashes due to metal fatigue. Each failure led to improved testing requirements and design standards. Today, when engineers design a pressure hull for a submarine, they account for every conceivable operating condition. Worst-case temperature, maximum depth, dynamic loading from depth charges or torpedo explosions, fatigue from pressure cycling, corrosion over decades of service, welding effects on local material properties. The testing is exhaustive. The quality control is absolute. The documentation is meticulous, because nobody wants to repeat the mistakes of 1944. Behind the metallurgy and the engineering and the tactical considerations, there were people. 28,000 German submariners died during World War II. That's a 75% casualty rate, the highest of any military branch on either side of the war. Not all those deaths were due to brittle fracture, of course. Most U-boats were sunk by depth charges, bombs, torpedoes, or gunfire. But some unknown number imploded due to hull failure at depths they should have survived. Men who died because of a materials science problem their commanders didn't understand. On the Allied side, over 30,000 merchant sailors died in the Battle of the Atlantic, torpedoed by U-boats, ships sinking in minutes, men drowning in burning oil or freezing water, lifeboats adrift for days or weeks, bodies never recovered. The steel weakness in U-boat hulls contributed to the Allied victory at sea. It helped turn the tonnage war against Germany. It allowed convoys to reach Britain with the food and fuel and materials that kept the war effort alive. But it's sobering to consider that the deciding factor in countless engagements wasn't courage or tactics or leadership. It was the behavior of crystal structures in iron-carbon alloys at low temperatures. Something invisible. Something the participants couldn't see or control. Something that determined whether men lived or died. Modern naval historians sometimes debate whether the Allies won the Battle of the Atlantic primarily through industrial capacity, code-breaking, technological superiority, or tactical innovation. The truth is that it was all of these, and it was also metallurgy. Small advantages compound. Every technical edge matters. For the individual U-boat crew member, none of this mattered much. They went to sea in steel tubes, hundreds of meters beneath the waves, surrounded by millions of tons of water held back by metal plates, 18 millimeters thick. They trusted that steel. They had to. Some of them died because that trust was misplaced. Not through malice or negligence, but because the engineering of the 1940s hadn't yet caught up with the demands being placed on it. In November 1944, in a testing facility in Teddington, British metallurgists discovered why U-boats were imploding. The steel became brittle in cold water. Cracks propagated catastrophically. Submarines failed at depths they should have survived. This discovery came from captured U-boats, from painstaking testing, from scientists who understood that understanding your enemy's weaknesses could save lives on your side. The Germans never learned what the British had discovered. The knowledge remained classified for years after the war. By the time it became public, it no longer mattered militarily, but it mattered scientifically. The lessons from U-boat hull steel influenced materials, science, structural engineering, and submarine design for generations. They contributed to our modern understanding of fracture mechanics. They saved lives in peacetime by preventing similar failures in civilian structures. Today, submarines dive deeper and safer than ever before. Modern nuclear submarines can reach depths of 500 meters or more. The steel in their hulls is stronger, tougher, and more reliable than anything available in 1944. But the fundamental challenge remains the same. Humans in steel tubes, descending into an environment that wants to crush them. The ocean is patient. It exploits every weakness. The price of failure is absolute. The men who tested that U-boat steel in Teddington understood this. They weren't just analyzing enemy weapons. They were discovering fundamental truths about how materials behave under extreme conditions. Their work made the seas safer for everyone who would come after. That's the real story. Not just about a flaw in German steel, but about how understanding material science at the deepest level can mean the difference between life and death, between victory and defeat, between engineering that works and engineering that fails when it matters most. The U-boat's fatal weakness wasn't discovered in combat. It was discovered in a laboratory, with careful testing, rigorous analysis, and scientific method. That's how wars are won, not just with courage and strategy, but with knowledge. And that knowledge, purchased at such terrible cost during World War II, remains valuable today. Every engineer who designs pressure vessels, every metallurgist who specifies steel grades, every inspector who checks welds stands on the shoulders of those who learned these lessons the hard way. The lesson is eternal. When you build something that must not fail, understand your materials completely. Test them in the environments where they'll serve. Never assume. Always verify, because somewhere, someone's life depends on it.